So today what we're going to do is the cross product to two vectors and see what that's all about. We're going to start out with the determinant of a matrix, which you need to know before you can do the cross product, or at least that's the way I do it. I'm going to try to go through this pretty quickly. But before we start that, basically what we're doing here is we're taking two vectors, like let's say this is, we got u here, and we got v here, and we're crossing them. We'll do u cross v. And when you cross them, you're going to end up getting a third vector, we'll call it w, that is perpendicular to each one, okay? And what that will do for us is it will allow us to do what's coming up next in lines and planes, okay? But mostly what we're going to be doing, and with this with later, where this is going to come in later is with the area of a surface. So we're going to take a surface and we're going to cut it into a whole bunch of, like a mesh here. And the area of the surface is going to be the cross product of vectors on the surface. And that cross product is going to be these W values. And the length of this cross product, the length of these vectors, and when we add them all up, we're going to find the area of this surface. Okay, so it's going to be really cool stuff coming. And but we need to know how to do this first. So let's get started with that. So like I said, we need to find the determinant of a matrix. This will help us out a lot. And if you haven't seen this before, you should have seen it in pre-calc. So I'm going to go through this pretty quickly. If you have, so suppose you have a matrix A, and it's given by A, B, C, D. The determinant, which is also known as A with, it kind of looks like absolute value bars around it, okay? Absolute value is the distance from the origin, but matrices don't have that. It's kind of a length of the matrix, so to speak. And so that's why we use absolute value bars, all right? All right, anyway, so the determinant is the cross product, is AD minus BC. So it's AD minus BC, like that. So for example, if you have A is 4, -1, 3, 7, the determinant of A, which you can also write, you can just write the matrix like this, 4, -1, 3, 7. That's going to be 28 minus a -3, which is 31. Okay, so that's the determinant of this matrix right there. So that's all well and good, but what happens if you have like a 3x3 matrix? So let's see what happens with that. This is going to be a little more complicated, actually. So for a 3x3 matrix, and this is where the cross product is really going to come in. Suppose we have a matrix A, and it's let's say it's A, B, C, D, E, F, G, H, I. Now I'm not going to go into the main specifics of why this works. I'm just going to show you what the determinant is. So the determinant of A is, you take A, I'm going to run along the first row, A, and I'm going to multiply times, I'm going to cross out the first row and the first column, and then what's left is this EFHI. So EFHI. And I'm going to take the determinant of that. So then I take the B, I'm still running along the first row. Then I take the B, but it's minus this time. So minus B, and I'm going to cross out the row and the column that B is in. Cross out the row and the column B is in. And what's left over is this D, F, G, I. So I'm going to take the determinant of that, D, F, GI. And now I run along, I find C. All right, so I take the row and the column that C is in and I cross that out. And I multiply times C, so plus C. And then I take the determinant of what's left over. So that will be D, E, G, H. Okay? And that will be the determinant of the matrix A, right there, whenever you do this. Now, I'm not going to, well, I guess we can write it all out if you want. This will be A, and then times EI minus FH, minus B times DI minus FG, plus C times DH minus EG, like that. Now, no one would ever memorize this. You just have to know I mean, it would be a good idea, let's just put it that way, to know the method, okay? So let's do this with numbers, and then we're going to get to matrices here in a second. Let me go down. Right, okay, so suppose we got A, and A is, let's do it numbers 1, let's make it -1, 3, 2, 0, 4, 1, 3, -5, and 6. All right. So we take the determinant of A. So determinant of A is, so we're gonna run along the first row. So -1 times the determinant. When you cross out the first row and the first column, you end up with 4, 1, -5, and 6. Like that. All right. Now the next term, this guy right here, this 3, is always negative. See, we had it negative up here. The B was positive right here. The B was positive, and then we made it negative. So the middle term is going to be negative. Well, that part is going to be negative. I don't know what the actual number is going to end up being. Anyway, so -3, we're gonna cross out the column and the row that 3's in, -3 is in. And we're going to write out what's left over, 0, 1, 3, and 6. And then plus, and this was a 5. Let me take the 2, so plus 2, that's the next term, and I'm going to cross out the row and the column that 2 is in, write out what's left over. Ends up being 0, 4, 3, -5. And so now you just take the determinant, you just finish all this out, which gives you -1 times 24 plus 5, that's this one, minus 3 times 0 minus 3, and then plus 2 times 0 minus 12. So this is here is 29. So -29. This is -3, so plus 9, and this is -24. So -24. All right, so it's 29 and 24 is 53. That's -3 plus 9. That will be 44. And so 44 is my determinant. Okay, so that's the answer. Right there, 44. Okay, so with that said, how do we do this with matrices? So what do matrices come in other words? Well, let's suppose that U is U1, comma U2, comma U3, and V is V1, comma V2, comma V3. So the cross product of these two is the determinant of this matrix here. So you write IJK on top, U1, U2, U3. So you can write the components of U here, and then the components of V below it. And now you take the determinant. So these straight up and down bars tell you that it's the determinant. So when you write this out, you get, all right, so we're going to take I times, and we're going to cross out the row and the column that I is in, and we're going to take the determinant of what's left over, U2, U3, V2, V3. All right, and now we're going to look at the J part, but J we're going to make negative, so negative J, and we're going to cross out the row and column that J is in, so that'll be U1, U3, V1, V3, and now K, we're going to cross out the row and column that K is in, so plus K, and we're going to write out what was left over, so that would be U1, U2, V1, V2. Okay, and now we find the determinant of this. Now this is just tedious. I mean, nobody would really want to do this by hand as far as like writing all this formula out, but I will, and you can skip this part of the video if you don't want to see it. So it's U2 V3 minus U3 V2. This is times I, and then this matrix here is so it's minus, and then U1 V3 minus U3 V1 J plus, and now the last one is U1 V2 minus U2 V1 K. Now if you notice, this is another matrix, right? It's got I, J, and K in it, and then it's got these numbers here in front. So this is another matrix, and we'll just call this, so I'm not going to call it W, this is U cross V. Not N, U. My U's look like N's. U cross V. All right, so let's do an example of this. So let's suppose that U is, let me draw this bigger. So let's suppose that U is, U doesn't want to cooperate. U is -1, 3, and 0. Well, I'll tell you what, let's make it 1, 3, 0. And then V, I want to see what this looks like graphically. V is, let's make it 2, let's make it 0. I'm trying to think of what this is going to look like. 2, and then 3, like this, okay? So we'll do the cross product, so U cross V. I had to think about it because I want to make it, the geometry look pretty cool. So U cross V will be I, J, K, and then 1, 3, 0, 0, 2, 3, that. So these are the components of U, and then the third row is the components of V. And so what we get here is we're going to cross out the I, so I. So it's going to be 9 minus 0 times I. Now, normally I would put the I here in front, like we were doing before. Like we did that before, we put the I in front. But it ends up off to the side anyway, so that's where I'm going to put it. So 9 minus 0 I, all right? So now we do the J piece. So this is minus quantity, now J, cross those out. It's going to be 1 times 3 minus 0 times 0. So it's 3 minus 0 times J. So let me take all this out now. And now for K, we're going to cross out the row and the column that K is in. So that's plus quantity. And now 1 times 2 and 3 times 0. So 2 minus 0. K, like that. And so when you clean all this up, you get 9I minus 3J plus 2K. Or the way I like to write this is 9, -3, and 2, like that. All right, and that's your cross product. So one way you can kind of check this, now remember, so the cross product is going to be a vector that's perpendicular to both U and V. Okay, so we're going to pull U and V into this. And let's graph all three of these. So let's see here. I think it'll fit right here. So we've got U equals 130. V is 023. And then W turned out to be 9, -32. And then, so W is just U cross V. All right, so now let's graph this real quick. I'm gonna turn off the recorder and graph it real quick. All right, so with the miracles of modern technology, it's magically graphed instantly. Essentially, U here is 130, so I went out 1 and then over 3 in the Y direction. All right, so let's remember where our axes are. This is the x-axis, and here's the y-axis, and then the z-axis is up here. So U is there, and then V, what I did was I went out 0 in the x direction, over 2, and then up 3. Graph V, and then now W here, W is U cross V, so U cross V. Now, W has to be perpendicular to both U and V, so I went, anyway, so let's start this. We went out 9, marched around to 9 on the x-axis, and then out to -3 in the y direction, and then up 2, so this is back 3, up 2 in the z direction, 9 to -3, and then 2. All right, so there's W. Now W has to be perpendicular to both U and V, and it is. I mean, it doesn't look like it, but it is. Okay, so now what you notice here, well, one rule is that we have to use the right-hand rule. We have to ensure that the right-hand rule is being taken care of here. The right-hand rule says that if you do U cross V, then if you take the fingers of your palm, the fingers of your hand, not your palm isn't the fingers. You take your fingers for U and your palm for V, then W will end up where your thumb is. So it's kind of hard for me to draw this, but if I put my fingers along U here and I curl them toward V and I'm using my right hand, then W is going to be along my thumb. All right, and so that's how this works. So that's the cross product for you, and that's how you do it. So we could try the cross product of 2 vectors in 2 space and see what happens there. And that'll probably be a little easier of a problem to look at. So let's look at that. So let's go further on in here. So I want to make that clear to you. So let's just do a quick example. So suppose that U is, I don't know, 2, 3, 0, and V is -1, 4, 0. Okay. So notice that this is in 2 space, all right? The z coordinate is 0 in both of them. So this is just in the xy plane. These are both in the xy plane. All right, so when we do the cross product, there's a quick way to do it. I want to show you that you don't need all the IJK stuff and you don't need the matrices. So basically what you can do is you can cross out the first column and do the cross product of what's left over, and that'll be your first vector component. So it'll be 3 times 0 plus 4 times 0, which will give me 0. Now, the next thing you do is you cross out the second column, and this time you go backwards with the cross product. So what we're going to do here is it's going to be the 2, -1, and 0, 0. So instead of going 2 to 0 and then -1 to 0, I'm going to go the other way. It won't matter because it's 0. So I'm going to go -1 times 0, but it will matter if it's not 0, minus, and then 2 times 0, which is just 0. So we have 0 here. And then I'm going to cross out the last one, 0, and I get 2, 3, negative 1, 4. Now I'm going to go in the correct direction this time. So we get 8 minus a minus 3, which is 11. So we get 11 here. Okay, so let's see what happens when you graph this. So I'm just going to graph it real quick. 2, 3, 0 over 2 up 3, 2 and 3. So that's this vector. So that's u. And then negative 1, 4, 0. So back 1 up 4. So that is going to be this vector here. So this is v. And now when you do the cross product, u cross v, your thumb is going to point in the z direction completely, because this vector, the cross product, has no x or y components. It's just a z component. So what's happening is, coming out of the origin here is the z vector, is that, sorry, not the z vector, the cross product, the w vector if you want, okay? And its length is 11, because the other two components are 0, all right? So if you want to look at this in 3 space, what's happening here is, I'm not going to draw them, well, maybe I will. Let's see, you got 2, 3, 0, negative 1, 4, 0. So 2, 3, 0 over 2 up 3, that would be like right maybe here. Here's u. And then negative 1, 4, 0, negative 1, 4, and 0. So that would be like here. Maybe this is v. Should be a little longer. V. And now when you do u cross v, you do u cross v with your right hand. So here are your fingers along u, and then your palm is along v. The cross product would send your thumb up this way. Okay, so this is u cross v, and in this case it was 0, 0, 11, which would send it up the positive direction. All right, so that's how the cross product works. So now let's talk about properties of cross products. So properties of cross products. Properties. The first property I want to talk about is probably the most important one. If you take the cross product, let me use u and v. The cross product of u and v, and you take its length, this is equal to the area of the parallelogram that u and v make. In other words, formed by u and v. Formed by u and v. Okay, so in v, get over here, v. So if you take essentially u and v, good old u and v. I think the book uses a and b a lot. It's fine. If you take u and v and then you look at the cross product here, u cross v, and the length of that cross product is going to be the area of the parallelogram formed by u and v. So if you just move this over like this, so this area, oops, let me use a different color. This area inside here is going to be the length of u cross v. Now, this uses a nice little argument using the area of a parallelogram. If you want, I'll pull this over. Since the length of the cross product is equal to the area of the parallelogram determined by a and b. I'll use u and v here instead, though. So let's pull this over. So what they've got here is they've got something like this. So here's u, here's v. Let's draw it the way they have it. And now we have a form of parallelogram out of this. So what they do is they make this right triangle here, and they look at this angle theta here. Now, the sine of theta, let's call this b for a second. The sine of theta is going to be, all right, so this is v, this is the length of v here. So the sine of theta is b over the length of v. So it's b over the length of v. So this means that b is the length of v times the sine of theta. Now, if I use a little bit of ingenuity and I draw that triangle that's over here on the left, and I draw it here instead, then what I have is a rectangle. So you have a rectangle here. So with that said, it's not the same rectangle. This b here, okay, can go here. And now this rectangle that I've drawn, its bottom length is the length of u. So all of, let me see here, let me do a different color. All of this is just the length of u. So what we have here is we have the area of the rectangle. Well, let's say the area of the parallelogram. Parallelogram is equal to the area of the rectangle. All right, and the area of the rectangle, though, is just, that's equal to u, the length of u, times b. But b was v sine of theta. So this is v sine of theta. And this here is u cross v, the length of u cross v. And so I just have to prove these two are equal, but it's the length here, length of u cross v. But once I do that, I'm done. So notice what I'm doing here. I'm already breaking protocol. I should have double bars here everywhere, double bars, but it gets really confusing. So I'm just going to write single bars and you'll know from the context. All right, so that's the proof that the area of the parallelogram is u cross v in brackets. Now, I didn't prove that this was true yet. U cross v, the length of it was the length of u times the length of v times the sine of theta. But what I would like you to do is to use the law of cosines to do that. Law of cosines to do that. See what you can do with that. I think it's probably in the book. All right, to prove. All right, so please know this formula. Try to derive it. You don't have to. Try to derive it. We're going to need this extensively. And then also know that the area of a parallelogram, the area is the length of u cross v. Okay, so now here's the deal. We had with the dot product, so recall u dot v equals 0 implies that u is perpendicular to v. Now this came from the fact that the cosine of theta is equal to u dot v over the length of u times the length of v, writing too fast. And if theta equals 90 degrees, in other words, they're perpendicular, then cosine of theta is going to be 0, which then would imply that the numerator of this fraction is 0. So that would imply then that u is perpendicular to v. All right. So, well, no, that implies that, and then you can go the other way if you want. All right. So with that, we can use that fact to prove something for this one. So here we have the sine of theta is, if you divide both sides by this u and v here, you'll get length of u cross v divided by a length of u across the length of v. Now, oops, sorry. Come back here. This is the length of u times the length of v. Now suppose that, now okay, so remember theta is the angle between u and v, right? You have u and v. Theta is the angle between them. All right. Geez, I'm not writing very well today. Suppose that theta equals 0. Okay, so if theta equals 0, then u is parallel to v. And if that's the case, also sine of 0 is 0. So this implies then if we take what's up here, this whole fraction, this implies then that u cross v, the length of that over x u length of v is equal to 0, which then implies then that the length of u cross v is equal to 0, because only the numerator is 0, right? So if you have, so what I'm using here is if a over b is 0, a must be 0. All right. So if that's the case, then if we have this fraction equal to 0, then the numerator is 0. And if the numerator is 0, that says that the length of this cross product is 0. Well, that would mean that if the length of the cross product is 0, that means that that w that comes off of u and v, that would have to be the 0 vector, okay? And since that's 0, that means u cross v must be 0, okay? So, and that would mean then that if u is parallel to v, then u cross v is equal to 0. That's that we prove. Now it is an if and only if statement. You can go each way. So to summarize all this, okay. All right. So summary of these two properties. If u is perpendicular to v, we know that u dot v equals 0 both ways. And if u is parallel to v, then this means both ways that u is perpendicular to v. Okay. I could have written, I should have written that the other way around. But anyway, you get the idea. So the issue now is, I mean, I guess I didn't make it clear. If u is parallel to v, let me go down. If u is parallel to v, then u and v, they look like this, right? Well, then the angle between them, since you can put u on top of v and v on top of u, let me make v a different color. So they're parallel. You can put one on top of the other, remember? So you can do u here and then v on top of it. V on top of it. And so the angle between them is 0. Okay? And so that's what's going on here. So what else? What do we have going on with the like applications of this or something? Oh yeah, this guy, the volume of a parallelepiped. So a parallelepiped is a parallelogram in 3 dimensions, kind of. Okay, and so I'm not going to go through the proof of this, but the volume is if the parallelepiped is formed by A, B, and C. So in other words, you have a vector. You have a vector A up here, and then C is here, and then B is here. Then the parallelogram formed out of all these. Let's take C out of there. C's down here. How do you draw this? Something like this. The parallelogram formed by all these is the volume is A dotted with B cross C, the length of that. Okay, so it doesn't matter which ones you do first, right? So you could also have the volume is C dotted with A cross B. Okay, you'll get the same answer. Doesn't matter. Okay, you're taking the absolute value. So this is absolute value this time. It's not length. It's absolute value because the dot product, this is a number. Okay, so you're going to A cross B, this is going to be a vector, some sort of vector. And so if you do a vector dotted with another vector, then you're going to get a number. And so it's the absolute value of the number. So I'll let you work through some examples of that. Okay, so maybe some of these would be good. All right, so now we talk about torque. So the torque is a measurement of force whenever it's kind of like a moment. Okay, so moment, if you heard of that in physics. Basically what it is if you have, let's look at this diagram right here. If you have a nut that you're trying to turn here with a wrench, okay, you have this, and the longer the wrench, the easier it is to turn the nut, okay, the screw. It's not a nut, it's a screw. Anyway, it could be a nut. So the length of R here, okay, so R is going to be a vector. The length of R certainly has something to do with the torque, okay, so we need this. All right. And now the force that is turning the wrench certainly has something to do with it as well. Okay, so we need also the length of the force, right? The magnitude of the force. And then the angle involved is certainly important as well, because we also need this, we need this, and then the angle involved we also need, okay? So we need all three of these to determine what the torque is. This as well, okay, right? So the torque, which is going to be coming out this way, okay? They're using tau for torque. How much this screw is turned, okay, or how easy it is to turn it is going to depend on the length of the wrench, the magnitude of the force, and the angle applied. Now, the angle applied is important because if, for example, the vector for the force is straight down, this theta is going to be greater. So we're going to get, let me use a different pencil. Theta is going to be max, so that's going to be max theta, okay? Now, if, on the other hand, F is this way instead, so instead of turning the wrench, you're just pulling on it, that'll be the minimum of theta there, okay? So that'll give minimum of theta, minimum theta. So the first one, this theta here, theta would be 90 degrees. And this other one, theta would be 0 degrees. So this is where sine comes in, because sine has a maximum at 90 and a minimum at 0, okay? So if we apply sine in here somehow with all these guys, we've got a good start on how to apply all this business to torque, okay? So let me kind of show you over here. All right. So here's the fact. Let me just give you the fact real quick. So fact, the magnitude of the torque is the magnitude of R times the magnitude of F times the sine of theta. Okay. So I'm going to, let's see where this comes from. Okay. So if I take F and I multiply times the sine of theta, okay, the minimum this can be is, well, let's say it's between two numbers, right? It's between F, magnitude of F. This is when theta is 90 degrees. So then sine of 90 is 1. So the sine of theta just becomes, this is equal to 1 there. And then it's also greater than 0, and this is when theta equals 0, since sine of 0 is 0. Okay, so whenever we looked at that the screw problem, you had the screw and it went out this way, spiral out, and you had the wrench going around it. coming out. And then you had the force coming down, coming out. So if the force is perpendicular, then it's going to be easier to turn this. If the force, so it's going to be easier to turn it, so it's going to be the maximum force, and if that's 90 degrees, this is 90 degrees, so that'll give me just straight on F. If you're pulling on the wrench instead, then the screw's not going to go anywhere, right? So that's when the angle, so theta is the angle between R and F, by the way. So here's R, and then F is this. Okay, now if F is over here, then this means that theta is 0. All right, and you're not going to get any torque out of this. You're not going to get any turn, okay? So it seems like it makes sense to make the magnitude of the torque the F times the sine of theta times R, because the part of F that is within, that is the part of F that is determining this torque will depend on the angle between R and F, okay? And so to multiply that times R will certainly give us an expression for the torque. Now, let me rewrite what I had there. So it was all gibberish. So the torque, the magnitude of it, is the magnitude of R times the magnitude of F times the sine of theta. But we know from before that this is just R cross F in magnitude. And so that's the magnitude of the torque. The torque is a vector, by the way, okay? It's coming out like that. Well, and this implies then that just the torque is R cross F like that. And there we have it, okay? So that's how that is determined. So you'll have some applications of that. And I think that's about it. That's about all the applications we have for this. So that's the cross product.